All right, in this video, we're going to take a look at an introduction to matrices, which is the plural form of the word matrix. And a matrix, by definition, is just a rectangular array of numbers. So we're not going to look at having to choose between the red pill and blue pill or anything like that. And I doubt Neo and Morpheus are going to be involved much, but you never know. Maybe we're in the matrix. And this rectangular array of numbers can be composed of vectors, which is how we're going to view most of our matrices and interpret them, or possibly scalars as well, if they're just, let's say, a single row of column with single number columns. So when listing the dimensions of a matrix, much like we did with the dimensions of a vector, we write the number of rows followed by the number of columns. So for instance, here we have matrix A, which has 3 rows, 1, 2, 3 rows, and 4 columns, 1, 2, 3, 4 columns. And much like with vectors, we usually enclose matrices in square brackets. However, it's also very common, just like with vectors, to see them enclosed in big parentheses. So it just depends on whatever notation the author, writer, whatever choose to use. So we have a 3 row by 4 column matrix, and much like with vectors, if we multiply that 3 times 4, like finding the area of a rectangle, that'll tell us how many elements are in the matrix. So each of the values, much like with vectors, called elements. So in matrix A, the element in the first row, second column, the intersection of the first row, second column, is this 6. So we use first row, second column is 6. If we have a really large matrix that has, let's say, 15 rows by 13 columns, we may have to use a comma, but usually, as far as our class is concerned, we're probably not going to get into any matrices that large. But in terms of where matrices are used by computers to store information. Pretty much everything on a computer is zeros and ones. So an image file that you have maybe on your camera on your phone or saved on your computer is just a giant matrix of zeros and ones. And depending on where those zeros and ones happen to be, you get a particular file type and you get a particular file itself. Spreadsheets like Microsoft Excel or Google Sheets, they also are visual displays of rectangular numbers that we can also program to do calculations for us. But if we just put in the information into a spreadsheet, for instance, like a grade book is just a giant matrix of numbers and scores for each student. That is a matrix. It's a giant matrix. So if there's like a class of 30 students, you could store their information for their grades and their scores that they get on assignments and tests into a matrix that has 30 rows, and however many assignments there are, that'd be you can use that as the number of columns. So we can think of a matrix as several vectors in the coordinate plane. So here we have the matrix 3, -1, -5, 2, -4, 3. And if we look at the columns of the matrix, we can form vectors in the coordinate plane. So for instance, we have the vector 3, 2, which is this blue vector. We have the vector -1, -4, which is this red vector. We have the vector -5, 3, which is this purple vector. So again, if we look at a matrix as vectors kind of in the same coordinate plane, we get this matrix. And in the next series of videos, we're going to take a look at matrix multiplication. But we got a few other things to talk about first. But example 4, we're going to graph the matrix 1, 0, and 0, 1. So let's take a look at 1, 0, 0, 1. So if I'm going to look at this as a vector, as a series of vectors, I have this vector here, much like we had started with this blue vector, 3, 2. And then we have another vector in this second column. So each column we can look at as its own vector. So if we graph this first column as a vector and this second column as a vector, it hopefully should look a little familiar. So 1, 0, we're going to go out to 1, 0. And then 0, 1, we're going to go to 0, 1. And if you recall from the last video, what we actually have here are the basis vectors I hat, which is this first column, and j hat. Again, pretend that I actually can draw this decently on a tablet here. So j hat. So we call a matrix like this, that is I hat followed by j hat. This two-dimensional matrix is an example of what's known as an identity matrix. An identity matrix. So we'll get into this identity matrices and all that stuff a little bit later, but for right now, just note that if we graph this first column, graph this second column, we get our basis vectors I hat and j hat respectively. So much like with vectors, we can add and subtract matrices under the condition that they have the same dimensions. So we need to make sure that our dimensions are the same before we add or subtract our matrices together, much like with vectors. So keep in mind things like a 2 by 3 matrix with 2 rows and 3 columns could only be added or subtracted from another 2 by 3 matrix. But if we have, let's say, a 2 by 3 matrix and we try to add a 3 by 2 matrix, which has 3 rows and 2 columns, even though they have 6 elements in each, they still are not the same dimensions. The number of rows of the first have to equal the number of columns of the second, or excuse me, the number of rows of the first have to equal the number of rows of the first or the second, and the number of columns in the first have to equal the number of columns in the second. I'm getting ahead of myself with this row column jumping across to the other matrix. And much like with vector addition and subtraction, to add or subtract matrices, we're just going to add or subtract the corresponding elements. So here we have matrices A, B, and C, and we're going to start with matrix A plus matrix B. Well, first let's check to make sure that we can add them in the first place. So matrix A is 2 rows, 2 columns. So matrix A is 2 rows by 2 columns. So get a little bit better too. Matrix B is 2 rows by 2 columns. And since the number of rows of A equal the number of rows of B, and the number of columns of A equal the number of columns of B, we can add these 2 matrices together. And it's really just, it's like taking the vectors and adding them separately. So we have, for instance, we could take -2, 0, add it to 4, -2 by taking -2 plus 4 and 0 plus -2. So if we do that, we get the vector -2 plus 4 is 2, 0 plus -2 is -2. And then, again, same thing with the second column, 3, 4 plus -3, -1. Just take 3 plus -3 and 4 plus -1. So 3 plus -3 is 0, and 4 plus -1 is 3. So here is our answer, and if we want to graph this as 2 vectors here, 2, -2, so 2, -2. Again, pretend that this is at the origin. For some reason, it's not wanting to do that. 0, 3 is going to be right about here, so that one looks a little bit better. So there we go. All right. Part B, let's take a look at matrix B plus matrix A. So we have matrix B is 2 rows, 2 columns. Matrix A, 2 rows, 2 columns. The number of rows of B equal the number of rows of A. The number of columns of B equal the number of columns of A. So we actually can add these 2 together. Here we're going to just essentially do 4, -2 plus -2, 0. That's going to give us this same first column. If we take 4 plus -2, it's the same as -2 plus 4, which is 2. Same thing with -2 plus 0 is the same as 0 plus -2, which is -2. We'd have -3 plus 3 is 0, and -1 plus 4 is 3. So we actually, for part B, get the exact same matrix with the exact same graph for it as we did in part A. And much like with vector addition, we say matrix addition since it doesn't matter what order we add the two matrices. If we do matrix A plus matrix B, we will get the same answer as matrix B plus matrix A. We say matrix addition is commutative. So it means it doesn't matter what order we add our matrices. So the answer to part B here, B plus A, is exactly the same as what we got in part A. So, all right, part C, we have A minus B, and I needed to remind myself of what those matrices were because my memory is not as good as it used to be. All right, so again, with adding and subtracting, we need to make sure the dimensions are the same, and since it's A and B again, and these are the same matrices as before, 2 by 2 minus a 2 by 2, we're allowed to do that because the dimensions are the same. So this time, we are going to take the values here in A and subtract the values in B. So we get negative 2 minus 4, which is negative 6. Again, we're subtracting. 0 minus negative 2 becomes 0 plus 2, which is 2. And then 3 minus negative 3 becomes 3 plus 3, which is 6. And 4 minus negative 1 becomes 4 plus 1, which is 5. Hopefully that looks like a 5. If we wanted to graph these vectors, we have negative 6, 2. I don't believe I gave myself enough space here. But go negative 6, maybe something like here, and then 2. This might be right about the point. 6, 5. We go, again, 6, I think, then 5. So it might be about here, and there we go. There's A minus B in terms of looking at the column of vectors. All right, part D, we have A plus C. So we have A plus C. Well, here, we haven't used matrix C yet. A is a 2 by 2. So A, matrix A. Whoop. Again, forgot to undo the arrow. Matrix A is 2 by 2, 2 rows by 2 columns. Matrix C, on the other hand, has 2 rows and 1, 2, 3 columns. So matrix C, we are looking at 2 rows by, well, that does not look like an R. 2 rows, there we go, by 3 columns. Maybe I need to slow down when I write. Here, the rows are the same, so that's good. However, matrix A has 2 columns. Matrix C has 3 columns. We cannot add these two matrices together. Their dimensions are not the same. So what's the answer to A plus C? If the dimensions aren't the same, it is not possible. It's not possible to add these matrices together. So it'll stop you right at the beginning if the dimensions of one matrix do not match the dimensions of another. All right, that about does it for this video. Thanks for watching. I'll